than the monomeric protein. It forms 3 dimeric species with distinct mobility, and it could be because there are formation of different disulfide bonds, like intermolecular disulfide bonds. And with increasing concentration of the oxidant, we saw oligomeric species too. So that means that these cysteines are involved in the formation of disulfide bonds. So we're talking about cysteines. So we wanted to do some more experiments, or we wanted to explore the cysteines, and what could be the role of these cysteines. In case of conformation of the protein, in case of DNA binding, and eventually in case of gene regulation, because the cysteines are located actually on N and C terminal extension, as I mentioned before. So what we did, we created 3 different mutants by substituting each cysteine with alanine. So we created C3S, C4A, and C169A protein mutant. We did SGS page analysis by incubating our cysteine mutants with increasing concentration of hydroperoxide copper chloride. And C3A and C4A, they form intermolecular disulfide bond, which is visible in the gel. But C169A, it doesn't form any intramolecular disulfide bond. That means that C169A is required for the formation of intramolecular disulfide bond. Now C3A, C4A, both of them, they are making 2 distinct dimeric species. But in case of wild type, we have seen 3 dimeric species. And now C169, it forms only 1 dimeric species. So that means that that 3 distinct dimeric species, formation of that 3 distinct dimeric species requires each of these systems, C3, C4, and C169. So it could be because either C3 or C4 are involved in the intermolecular disulfide bond formation between 2 oyster dimer alone, or it could be because of the combination of intramolecular disulfide bond and intermolecular disulfide bond. And intramolecular disulfide bond requires C169. So now we know that these cysteines are involved in the disulfide bond formation under the conditions of oxidative stress. Thus, there is a possibility that the cysteines are actually involved in the conformation of the protein. They are not just flapping around like on N and C terminal extension. Okay, so we were, after seeing this one, we are interested to see that whether cysteine mutation is affecting DNA binding affinity. So the idea was that if these N and C term extensions are not disordered, if they are docked in the protein core, what would you expect to see? That if you are interrupting with any of these amino acids, that may affect DNA binding, right? That may affect the conformation of the protein, eventually DNA binding or gene regulation. So that's a possibility we're talking about, right? So what we did ENSA by incubating EMRB promoter sequences with either C3S, C4, increasing concentration of C3S, C4A, or C169. As you're seeing here, that each of these mutants still form 3 complexes with the cognate DNA, okay, just like a wild type protein. But if you're not looking at the concentration, you will not see that much difference in the gel, basically. But when we calculated KD, dissociation constant, so the KD for C3A is 17 nanomolar, and KD for C4 is 23 nanomolar, which is higher than the wild type KD, 7 nanomolar. Okay, that means that this protein, substitution of this cysteine 3 or cysteine 4, that affects DNA binding affinity. Okay, just to mention, when the KD goes up, affinity goes down. Now, the most interesting thing that we have actually found here that in case of cysteine C169A mutant protein, the KD changes drastically, like 539 nanomolar, which is way higher than the wild type KD. Okay, so when we are actually deleting this cysteine 169, or we are substituting this cysteine on C terminal extensions, that leads to the collapse of the protein, kind of thing, but that leads to the destabilization of the protein and eventually affecting the DNA binding. So further, to determine that whether the cysteines are playing structural role or not in case of OSTR, we did a thermal stability assay using each of these mutants. So C3A and C4A, each of them show increased denaturation temperature in comparison to wild-type protein. And again, it's proving that these N and C terminal extensions are not, disordered, or they are not slapping around. They are docked in the protein core. And that's why when we change anything in those extensions, that affect the protein structure. And this is actually for C3A, the reduced protein is this red dotted line, and in case of C4A, the reduced one is the green dotted line. Okay, and temperature should be clear. Now, what happened in case of reduced C169A? So when we measure thermal stability of reduced C169A, that was really surprising in a sense that you see the initial fluorescence, okay, this orange dotted line, initial high fluorescence and the rapid decline in the fluorescence, and there is no fine melting transition. And this feature is telling us that C169 is not properly folded. That's why their hydrophobic core is already exposed, so C4 binds and it shows the initial fluorescence, high fluorescence. Okay, so now we know that this cysteine 169 and cysteine C3 or C4, which are located on N and C terminal respectively, so they are actually required for the stability of the protein. That means that these N and C terminal are actually required for the stability of the protein. So interesting part was, in presence of ligand, suppose zinc, C169A, that restores its compact folded structure. Okay, and we see this fine melting transmission here. Okay, and the denaturation temperature of this protein in presence of ligand is approximately 6 degrees Celsius, which is higher. Okay? So that means that this protein gets back its folded conformation in presence of ligand. Now going backward, when we oxidize C4A or C3A, this purple dotted line and the blue dotted line, we saw that there's a high initial fluorescence with a rapid decline in the fluorescence, and there is absence of melting transition. So it depicts that oxidation of either of these mutants, C4A, C3A, that destabilize the protein. So from all this data, you can say that these N and C terminal extensions which are harboring these cysteines are not disorganized, they are contacting with the protein. So what we propose is this C terminal extension, coming back to this electrostatic surface potential of rest here. So what we propose is this C terminal extension is interacting with this positively charged patch, and this cysteine of C terminal extension, the thiolate anion of this cysteine is contributing to neutralize over positivity charges here. Okay. Now, when we take out the cysteine, thiolate anion is lost, and that's why we see the destabilization of the protein. Again, when we oxidize C3A or C4A mutant, when the C169 is still there, right? And it can form intramolecular disulfide bond with either C3 or C4A. So when we oxidize C3A or C4A, again, thiolate anion of C169 is lost. And that's why you see the destabilization. So this thiolate anion of cysteine is actually contributing to neutralize the positively charged patch here. Now, in presence of zinc, we saw that C169A, that restores its folded structure, right? So the possibility is zinc coordinates with the amino acid residues on N-terminal extension and near this positively charged patch, and thus bring in these vicinal cysteines toward this positively charged patch. Okay. Now this cysteine thiolate can also contribute to neutralize positively charged patch, and thus the cysteines are contributing to the stability, to maintain the stability of the protein. So from here, we concluded that N and C terminal extensions must contact with the protein core. They are not actually disorganized. So the key upshots is OSTR binds to the upstream promoter region of EMRB and thus represses expression. The N and C term extensions of OSTR is not just flapping around, they are contacting with the positively charged lobe of this protein. In presence of sublethal dose of gentamicin, when OSTR goes down, EMRB is upregulated. EMRB is the primary exporter for trimethoprim. EMRB also exports maltosic acid and tetracycline. But in absence of EMRB, there will be accumulation of antibiotics, suppose tetracycline, and that can induce one RNA compound named AMRB, and eventually will transport it to AMRB. And this research we have published in the JDC in 2018. So now, when we talk about the transcription regulation of the gene expression, it's a very complicated process. It doesn't actually involve only one transcription factor, or it doesn't involve only one step process or something like that, right? There are actually web of intrinsic mechanisms to regulate these genes which are involved in the efflux pump, or which are involved in this virulence of bacteria. So I'm going to talk about a little bit of web of intrinsic mechanisms to regulate these efflux pumps. You may remember that this OSTR is located on a genomic locus where two other genes are also there. And we already know that OSTR is regulating EMRB expression by binding to the promoter sequence and thus repressing its transcription, right? So what's going on with this HIP encoding hypothetical protein and RND, which is encoding RND efflux pump? Whether OSTR is also regulating their expression or not. To answer this one, we determined transcript level of HIP and RND in wild type and delta OSTR. As we're seeing here, that HIP is approximately 2.5-fold upregulated in delta OSTR, and RND is approximately 2-fold upregulated in delta OSTR. So that means that OSTR is not only regulating EMRB, but also regulating these divergently oriented genes, HIP and RND. Okay. We know that OSTR is the transcript repressor of these genes, so whether OSTR is binding to their promoter sequences or not, that was the next question. So we did EMSA by incubating HIP promoter region with increasing concentration of OSTR, and as you see here, that OSTR forms at least 4 complexes with the HIP promoter sequence. That means that OSTR is binding to the HIP promoter, and we calculated KD value that is approximately 65 nanomolar, which is actually higher than the KD of EMRB promoter. So that means that OSTR is binding to HIP, but it has lesser affinity for HIP promoter in comparison to the EMRB. We also did EMSA by incubating RND promoter sequences with increasing concentration of OSTR, and the KD of this EMSA is saying us, and is telling us that OSTR is binding to RND promoter, but it has lesser affinity in comparison to the HIP promoter and EMRB promoter. But OSTR is binding to each of these promoter sequences and thus repressing their expression. Okay, so now we know that OSTR is a transcription repressor of 3 of these genes. We know that RND and EMRB are 2 of the major efflux pumps in bacteria which exerts antibiotic resistance because it can extrude diverse compounds like antibiotics or disinfectants, right? So there's one more gene here in the same genomic locus. We named it HIP because it encodes for hypothetical protein. This genomic locus is conserved in pathogenic bacteria, suppose Pseudomonas or Sinusiation. We're just wondering, okay, what's going on with HIP? I mean, why HIP is there? We looked into the predicted feature of this protein, and we have seen that hypothetical protein is positively charged, highly positively charged, first of all. It contains, it has alpha helical content. So we were wondering that it may bind to the negatively charged DNA. So what we did, we obtained HIP transposon mutant, where the transposon started at 140 position of the open reading frame. We verified this one, and then we measured RND and EMRB expression in delta HIP. And as we're seeing here that RND is upregulated approximately 2-fold in delta HIP, whereas EMRB is upregulated approximately 14-fold in delta HIP. That means this hypothetical protein is not actually a hypothetical protein, it's a transcription factor, It's a transcription repressor of RNG and EMRB. And this is really exciting because in the protein database, this hypothetical protein is considered as, it is mentioned as hypothetical protein, okay, not as a transcription factor. So we discovered this one, that this is actually a transcription factor. And there is no known protein family for this hypothetical protein, so it could belong to a novel protein family. So we need to look into that too. So now we're interested in this HIP gene, which encodes for a transcription factor basically. So what we did, we were interested to see that HIP is autoregulatory or not. So we measured HIP expression in delta HIP, and in comparison to wild type, there is no significant change in the HIP expression. So that means that HIP is not actually autoregulatory. Just to mention here, we designed the primer based on the upstream sequence of the transposon insertion. Now, you may remember that gentamicin represses OSTR expression. And OSTR and HIP, both of them are actually controlling expression of the same target genes, RNG and MRB. So we're wondering that whether gentamicin is also repressing HIP expression or not. And yes, it was right. As expected, we have seen that gentamicin is also repressing HIP expression. Okay. So from this data, the basic takeaway is OSTR is not only OSTR is a transcription repressor not only for EMRB but also for the HIP and RNG. And the most exciting thing that we got from this gene expression analysis is that hypothetical protein is a unique transcription factor which regulates RNG and EMRB. As we're interested in this hypothetical protein, so the next step would be the expression and purification of the hypothetical protein. So we have actually already done this expression of hypothetical protein in E. coli strain. We have done that. So I'll work on I'm actually working on purification now. And we would like to see interaction, whether there's an interaction between the OSTR and the hypothetical protein, as they are the transcription factors which regulate same target gene, RNG and EMRB in this case. We'd like to complement delta HIP mutant, but in this case, obviously, we're not going to use the gentamicin cassette containing residence cassette containing plasmid. We're going to use something else. Now, last but not the least, many of you have heard about a very famous transcription factor, OXCR, that responds to oxidative stress and that regulates different genes, right? So in another study, it has been found that OXCR is the transcription activator of the HIP, our gene of interest. And we determined that sublethal dose of gentamicin represses OXCR expression. So the scenario is something like this. Gentamicin represses OXCR expression, and OXCR is the activator of HIP, so HIP is expressed too, and so the OSTR. So we are interested to see that whether there is any tight joint collaboration, or like whether there is any tight joint like coordinations going on between these three transcription factors to regulate RNG and EMRB. Okay. And that would be all. So I'd like to turn on the light first. So my PhD journey is, it's a memorable journey. And it was not possible without having some adorable people in my life. I'm getting emotional. I'd like to thank them from the bottom of my heart. First of all, Dr. Anne Grove, my professor. Thank you, Dr. Grove, for having me and for giving me the chance to work in your lab. That's a very formal way to thank me. I'm not going to do that. I'm going to say what's coming from the bottom of my heart. So, Dr. Grove, I met Dr. Grove when I was going through very turbulent situations in my life. And she really held my hand and she said, okay, welcome to my lab. And it took a lot, as she mentioned, that with this project, ups and downs and things like so unexpected cake and all those. but she was always there to motivate me, and actually every student. It doesn't matter whether her student or from other labs, she always motivates grad students. She is someone, she's not an awesome PI only. We actually tell her like every now and then, you're an awesome PI. Yes, she's an awesome PI, that's true. But you know, the most interesting thing that I like about her is she's an awesome human being. She understands other situations and she respects others' perspective. So thank you, Dr. Grove, for being me in your lab, and you are a blessing in my life, and I just love you. Sorry, I'll be like, read whatever it comes in my mind. I'm not saying that. I did not prepare any speech for this. Okay. I want to thank my committee members, Dr. Tonsi, Dr. Dover, and Dr. Jerry Folu. I pronounced it right. Dr. D, basically. So for being my committee members and for being here. But whenever I asked for help, they actually helped me. They were there for my well-being. And thank you, Dr. Tonsi, for arranging that guild ride. That was really needed at that time. Thank you so much. And Dr. Donor, I don't know whether you know or not, I actually use the lab facilities. Thank you so much for that. Sometimes you're there, sometimes you're not. So I don't know whether you know that or not. He was like, oh, okay. Okay. And though Dr. Lane is not here, but I would like to thank Dr. Roger Lane. We share similar kind of sense of humor, and he's very kind and helpful, and he always inspired me throughout my PhD life. And I want to thank all the people who is working on the fifth floor Chopin, and that's a family to me, because I mean, at least 16 to 17 hours I actually spent in my lab or on that floor or in this campus. So this is a family to me. And I want to thank Genomic Facility for letting me use the facility. And of course, Department of Biological Sciences. So here I'd like to mention that I feel very lucky to be a part of the Department of Biological Sciences at LSU. Obviously, PhD is to us, PhD is something like great, right? But this department is so helpful that I actually tell my juniors that, okay, if you want to apply here too. And let's see, this department is really helpful. All the people here, starting from the grad school lab, different other labs, and all the people here, they are very, very helpful, and they are very kind. And frankly speaking, I still live in New York too. I'm not saying bad about New York, but I think people are more friendly here in this department. So, yeah. I'd like to, I think, you can see, right? You can see yourself here. I'd like to thank all the past and present group lab members. So here, soon, Brennan, my undergrad. Brennan, you just did an awesome job, frankly speaking. And he's going to med school very soon. He's going to treat me free. Because he has name in two of my papers, so yeah, he has to. And thank you, Sanjay, thank you, Arpita, for being here. Thank you, Matt. So all the other members that were missing here, thank you so much for contributing in my research work, directly, indirectly. You guys are awesome, frankly speaking, and this is an environment that we, this is a friendly environment. Yes, there's obviously some fee, but yeah, this is a very friendly environment, and I appreciate your presence in my life. Okay. Last but not the least, my adorable friends, Runa, Randy, Hannah, Wes, who have seen me, my journey, personal, professional, from the very beginning of my PhD life. Runa Randy is here. Thank you so much, guys, for being here. I just love you. And thank you, Matt. Very distant guy, but I know him. Thank you, Manali. I call her baby doll. And thank you, George. George, a gentleman. And Nathan. I mean, he is someone like really helpful. Whenever I needed help, whenever I asked him anything, he will just pull my leg first and then, okay, I'm gonna help you. So thank you so much, everyone, for being here and for enjoying me. Thank you so much.
questions for Afsana?
So the cysteine 169, did you mutate it to any other residues besides alanine?
Not really. We substituted cysteine with alanine only.
Do you know of any other mutations that could help with your hypotheses?
We could use, I think, sure, maybe some negatively charged residues to see. Aspartame.
Yeah, good job.
I know, I think.
Are you okay, Mama?
I tried a softball.
I'll save the hard questions for later. So, now that we have a function, are you going to get to name the hypothetical gene? Do you have a name in
Do I have a name for that now?
Yeah.
I'm going to think on that. Because we have to characterize the protein first, and how it's regulating, what's the nuclear balance of the catalysis.
But the poor thing can't go through life uncalled.
I was actually discussing this with Dr. Roche. Should we call him or something else? So yeah.
Other questions? All right, thank you very much for coming, and then the committee will stay here, and Afsana